So we're going to look at an analysis of a PIV laser. This is a laser used in particle image velocimetry, and what the application really is measuring the velocity of a fluid, of fluid flow. You drop some particles in this fluid while it's moving, and say it's air. Then we use a laser to illuminate the particles. We illuminate the particles twice within a few microseconds. We take images. We take the image of the first illumination and the second illumination. We're able to compare the particles' positions such that we can get the distance the particle has traveled. We know the time between the two images, and we can calculate the velocity of the fluid. It's a lot easier said than done. Okay, the laser in itself is really typically are two heads. I have seen a laser built to do this where it would fire two pulses within a few microseconds of each other, and then it could do this at 10 hertz. So it would be what we would sort of call group pulsing. But most of these PIV lasers that we run into are two heads. So the first head fires, and then a few microseconds later the second head fires, and that's where you get your two images of the particle motion in the fluid. Now the beams from the two lasers are made collinear, so they're running along the same optical axis in the output. And since the pulses are within a few microseconds of each other, we're going to add the two energies together. Okay. Now let me explain why. There's this, if you look at table 1 in the standard, you'll see something called Tmin. And for this wavelength, 532, right here, 532, Tmin is 5 microseconds. And what we mean by that is any two pulses that arrive within 5 microseconds or arrive within Tmin are treated as a single pulse. The reason is when the first pulse is absorbed by your biological tissue, if the second one is absorbed within 5 microseconds, there has not been enough time for the heat to move from the energy of the energy absorption of the first pulse. So all the heat is still sitting right there where the pulse was first. The first pulse was absorbed. The second pulse comes in, and so you just are adding twice the energy into that, creating twice the heat. And now, once you're past 5 microseconds, the heat will start migrating out. But within 5 microseconds, the heat doesn't have time to move. It's called thermal confinement. Okay. So if you look at if you look at the table in that's table 5E for 532 nanometer wavelength, and you look at 10 picoseconds to 5 microseconds, you'll also notice that across that whole range that the MPE is 2 C sub E times 10 to the minus 7th joules per square centimeter, and since we're looking at this as a point source, C sub E is 1, so the MPE is what we get right over here for rule 1, 2 times 10 to the minus 7th joules per square centimeter. Okay, and as you can see, this analysis will be driven by rule 1. Right. But because it is the same, all right, it doesn't matter whether this pulse, if the pulses arrive in 2 microseconds or 4 microseconds or something like that. As long as they're within 5 microseconds, we treat it as one pulse. And I would say even if it was outside this 5 microseconds a little bit, I would still treat it as a single pulse, adding the energies together just to be conservative. Okay, so we have a 532 nanometer laser. We've added the two pulse energies together to get 400 millijoules. The pulse duration is 8 nanoseconds. The repetition rate is 10 hertz, and we're using the NC default exposure for visible light of 1/4 of a second. Now, let's take a look at the beam conditions here. Because in order for this system to work, we need a sheet of light. So imagine taking your laser pointer, pointing it at the wall, and you get a spot, right? Now what we're going to do is take an optic, and all this optic does is create a higher divergence in one axis of the beam. So it stretches it out, but it doesn't do anything to the other axis. Okay, and it's called a PAL lens. That's the best optic to use for this type of application. Okay, so it stretches one axis, leaves the other axis alone. If we were to shine that on, if we had that lens on our laser pointer and we shined it at a wall, what we would get is a line. Okay, now if you turn all the ambient lights off and you have enough power in your pointer, what you'll see is a sheet of light. It will be triangular in shape, and it will be a sheet or a plane of light, right? Because it starts from your laser pointer at, coming out of the output aperture of your pointer, so it's like a point. We spread it in one axis, okay? And so you have this triangular sheet or plane of light. And that's what the PIV laser does. So we need to model that. And the way we do that is, for PAL lenses, the best thing to model in is a rectangular top hat, because we would like a uniform distribution across that line or across the fan. We can use either 1 over E or 1 over E squared. The major axis we set at 1 millimeter. That's typically about what it is. And then m squared we'll set as 1. We'll set to 1 because we're going to be conservative here. That will give us the lowest divergence. So you can see over distance, this beam isn't going to change much. It's going to stay 1 millimeter. And the only distance we're going to be looking at is, say, between a half to 3 meters, something like that. So you're not going to get a lot of change out of it. The other axis, we just use something small, and because it's the minor axis, we set it a little smaller than what we've set in the major axis. But it doesn't really matter what you put in here. You could put 0.1, you could put 1, because this axis is going to be dominated by the divergence. It's a huge divergence. It's 20 degrees, 349 milliradians, and we can see that if we were looking at a meter out, we would have in our major dimension, or what starts out as our major dimension, a beam diameter of 1.2 millimeters. But boy, in our minor dimension, we have a line length of 349 millimeters. So you can see how this is modeled a line pretty well. And so realistically, we've modeled this fan or sheet or plane of light. Okay, so the OD at the observer range is reported here. The worst case OD is 6.7, but that's not going to happen. You can't get all this light in your eye through the limiting aperture. You can only get part of it because, remember, we're spreading it out, right? So if we said we were looking at 1 meter, how much would we be transmitting? About 2%. And so out of 400 millijoules, we'd be looking at, let's see, transmissions, there we go. We'd be looking at about 8 millijoules going through our limiting aperture of 7 millimeters. Okay? All right, so we have this modeled out fairly well. This is how you do it. And then you can go about and do the hazard analysis, take a look at wherever you'd like the observer to be standing, figure out the OD. You may just want to go to the worst case OD. We have an NOHD from this particular laser of about, let's see, 1,000 meters. You'd say, well, that doesn't seem possible. Understand that this is a whopping pulse in this thing. And we're not really spreading one axis very far at all. So when we take a look at over here, let's look at the peak power. You have 50 megawatts of peak power in that pulse. So yeah, this is going to be able to have travel quite a distance and still be a hazard. And it's because of this pulse, right? And yeah, 50 megawatts is, that's a lot of peak power. So it shouldn't be a surprise what the NOHD is here. Now, we can look down here, take a look at the ocular MPE. It's 2 times 10 to the minus 6 watts per square centimeter. That comes from the rule 1, 2 times 10 to the minus 7 joules per square centimeter multiplied by the repetition rate. We can see that here if we click that. That's it right there. Okay, the skin MPE is about 200 milliwatts per square centimeter. The times skin MPE for where the observer is standing is about 14 times above the irradiance. The irradiance of the laser is about 14 times above the skin MPE. So yeah, this would be a little bit of a hazard to you if you were that close to it. Okay. And that's really about all there is to look at on this laser. But it's if you're in a university or research labs, it's more than likely you'll run across one of these lasers, and this is how you go about modeling it. If we were looking at barriers to help contain this, we can see the radiant exposure at 1 meter, but we'd want that barrier further out. And I'm going to say it's probably going to be about, let's say, 3 meters out. All right, let's put it at 3 meters out. And we can see that we would need a barrier that could withstand about 17 millijoules per square centimeter. And for irradiance, you need to withstand a couple of hundred milliwatts per square centimeter. So at that kind of distance for this type of laser, you don't need a barrier that's going to withstand a lot. It just needs to block the visible light pretty well. Okay? I think that's about it. Oh wait, there was one other thing we wanted to look at here, and that is what happens if we caught a 4% reflection off an optic surface. What would that look like? Because, most of the time that's what happens. People, when an accident occurs, it's from a reflection off of one of the optics. Now we're saying it's going to be about 4% off the optic, and that would be about 16 millijoules. So all we'd have to do is come over here and change this to 16 millijoules, and we could see the results here for a reflection, a 4% reflection off of a glass surface. All right, I think that's about it.